All right, so what we're going to want to do here is we're going to want to set up our instructions on how we integrate in spherical coordinates. So again, let me get a coordinate system here. Go XYZ. And there will be our y-axis, our x-axis, and our friend the z-axis. We're going to look at some chunk above. In fact, I think we'll work our way with the instructions with a problem. We'll center a cone on the origin. So we're going to have a cone that's bounded above by a sphere of radius 1. And we'll make our little rays L and all the things that we need to do within there. So what we'll first do here is let's make our cone in yellow. It's kind of coney. So we have the sphere of radius 1 binding a cone. And so find the volume of the cone bounded above by the sphere of radius 1. So rho equals 1. And so what we're going to do is instead of having a projection down into the plane, we'll have a projection of the body down into the plane, but we're not going to emanate from the plane itself. We'll emanate from the origin. So let's make our kind of ringed segment. So this is our region D, our cone that's bounded by a sphere of radius 1, and then projected down onto the plane. So its shadow down here is R. Right. R is the shadowed region that comes down from our object here. So we have R. And what we want to find is we want to find the ray M that punctures out. So we have some ray M that punctures out through our solid, and we need to know where it enters and where it leaves. And so in this case, it's going to enter at rho equals 0, and it's going to leave at rho equals 1. So we'll put d rho out there. So that radial ray rising up through the cone, and then working its way across the cone. Then the next thing we need to figure out is we need to find the phi limits, or what angle measures phi in here. And so we have to figure out how phi interacts with the cone that we have. And I think it's worth noting that phi is going to start at 0. It's going to start at 0, and it's going to work its way out for the cone. And a cone, let's see here, look at my description of the cone. And we'll look at its projection coming across. 1/3 base times height. Let's see. If we get a right triangle here, let's see. The cone comes out. That's still radius 1. So this is radius 1 out here. And that works back to be radially. I want to make a sketch here. Pardon me 1 second here. We're looking at pi over 3 for the angle that phi comes to. And then in our last thing we want to do is we want to look at what the theta rotation will be. And in this case, theta is going to make its way around from theta equals 0 to 2 pi as we make a complete rotation. And then we need to put in our translation units. Rho squared sine phi. And so if we do our integration terms, remembering that this is what we need to do our coordinate transformations for our differentials. And so the differential in volume, the dV, for spherical coordinates is rho squared sine phi, d rho, d phi, d theta. So our first integration will be within terms of rho. So that's going to be rho cubed over 3 sine phi evaluated from 0 to pi over 3 d phi d theta. And that'll leave 0 to pi over 3. Whoops, that's not 0 to pi over 3 here. That's 0 to 1. And 0 to 2 pi. So that's going to give 1/3 sine phi. So I'll bring that 1/3 out front. And then we have sine phi. That's going to become negative cosine phi evaluated from 0 to pi over 3 d theta. So that's going to be 1/3. Let's see, that's going to be pi over 3 is 1/2 minus 1. Let's see, it's going to be minus 1/2 plus 1 which is going to be, what is that? That'll be 1/2. I guess I can do my integration now. So this will be 1/2 theta evaluated from 0 to 2 pi, or pi over 3. So finding the limits, the really big difference is just this ray m. It's going to emanate from the origin and puncture our solid in spherical coordinates. And then we look at the angle back to this ray m that it needs to make to get to the far side of our solid, region D, and then the rotation that scoops up. notice how this works really nicely for things that are centered around the origin. All right, let's do one more. I'll put that to a separate video here.